Afternoon, Tila. No mic on Tila. Okay, all right. So, afternoon again, everybody. We are going to be, there she is. We are going to be starting or continuing on with module one. So, we're going to go on to electricity and magnetism. Not electricity, we're going to do magnetism and electromagnetism. This part of the syllabus sounds familiar to you all, but it's a brand new world. You're going to look at a whole other new aspect of magnetism. You're going to look at it in more detail. We're going to continue with the equations that make words. All right, that's why I like this topic. We have equations that make words. So you already did I never. Okay, just I never. But we're coming up to the other words of just now. So just reading through, I did post in the Google Classroom your syllabus section. So this is the syllabus that applies to what we're going to be doing probably over the next 2 weeks. Yeah, so we should be finished with module one by Diwali. Yeah, Diwali is next week. So yeah, by next week we should be finished with module one. So that's reading. We have here, let's move this to the side. All right. So magnetic fields, you have to one, explain magnetic flux density and the Tesla. No, we're not looking at the Teslas and the car. This is far older. Tesla derives from one of the greatest physicists of all times. All right, so if you want to read up, please go and read up on Tesla. Nikolai Tesla. All right, read up on Nikolai Tesla, one of the greatest physicists of all time. Okay, so we're going to have explain magnetic flux density and the Tesla sketch magnetic flux patterns due to a long straight wire, a flat circular coil, and a long solenoid. Then we have to use expressions. We have to calculate the magnetic flux density for 3 different situations. We have to look at that involving a straight wire, the center of a flat circular coil, and an infinitely long solenoid. So that's it. This we should finish more than this today. All right, going down, we have magnetic forces. We're going to use Fleming's left-hand rule. You all should remember your left and your right-hand rules. We're going to use the equation of force is equal to Bill, and then there is, all right, we have force is equal to Bill and force is equal to Bill sine theta. Obviously, we're going to look at angles involved in there. So that's actually the first equation up. You're going to see this at the very first start. Explain how force in a current carrying conductor can be used to measure the flux density, right, by means of a current balance. So this is going to be homework to read up on a current balance. Sorry, that was WhatsApp. All right. Wonder if WhatsApp is going to work. Nope. All right. So we have current balance. You are going to have to read up what this is, and then we're going to explain it because I want you all to be able to explain this why. I want you to be able to explain it to have a good understanding of a current balance. It has come for exams already. All right, it was a long, complex diagram, but it wasn't too hard. It just was long and complex looking. Predict the direction of the force on a charge. We're going to use the expression of force is equal to BQV, right? And whatnot. So after there, we're going to go to the Hall effect. Hall effect is a new topic. This works out our next word equation, magnetic induction. All right, and somewhere inside here, we have to also work in transformers. I don't know why the transformers is not inside the syllabus, but it's in the exam. It's every year in the exam. So we'll do transformers, down to really in depth. You're going to see how we derived formulas for transformers. It wasn't just random. They decided to take number of turns and find voltage and get an equation. There's actually a reason why they are related. Okay, so we're going to stop share screen here. So we're going to look at magnetic fields. Reading from the handout. Electric field strength E is defined as the force per unit charge. Similarly, an analogous quantity for magnetic fields is the flux density or magnetic induction, B. So the symbol here is your magnetic induction. All right, flux density is defined as the force acting per unit current length or force acting per length on a conductor which carries unit current and is at right angles to the direction in the field. It's a really long, complicated way of saying it is the force if you have a length of wire. If we have a length of wire, we have a length of wire that is 1m. All right. Magnetic flux is simply when one length of wire carries 1 amp of current and exerts a force of 1 Newton. So, you know, when a wire is within a magnetic field, as long as we have a wire, current carrying conductor that's in a magnetic field, it's going to experience a force. So it experiences a force of 1 Newton, right? Acting per unit length. Remember, the unit means 1 meter. Acting per unit length, per unit charge being 1 of your current, you're going to get your magnetic flux density. So let's see what it actually, how you can work it out. Magnetic flux is measured in Teslas. So this is our brand new unit. All right, magnetic flux is always measured in Teslas. Please note when you all have to work out your magnetic fields, you always move out of the north and into the south. You always have to remember that when we have our magnetic fields, that direction is extremely important when we have to work out our questions and work out our directions and whatnot. We have to remember the exact directions of current that magnetism flows in. Also, if we have two magnets, please remember if we have a north and if we have a south, it comes out of the north and goes towards the south. We're going to have to remember this when we are doing our left and right hand rules. So please remember your directions carefully, out of the north into the south or north to south. Okay, lots of students remember north to south, but they usually mix up this area here as in which one it is coming out of and which one it is flowing into. Okay, so using Fleming's left-hand rule, just to revise, you all should know, let's see what's Fleming's left-hand rule. All right, using your left hand, if we have our thumb, our index finger, and our second finger, what does our thumb represent in Fleming's left-hand rule?
This is current.
No, your thumb.
Direction.
Force.
What does your thumb represent in Fleming's left hand? Remember, you have
The
them. They are
the
right
magnetic
angles.
pole.
The field,
But I know
magnetic
those are
field.
What?
the magnetic the induction the north or south pole, right?
No.
No?
No.
The force.
The force. Thank you very much. Your thumb represents the force exerted on your conductor. What does your index finger represent for Fleming's left hand rule?
The field.
The magnetic field. All right, this is your field. And what does your second finger represent?
The current.
Current. All right, so remember, we always keep our fingers at right angles to each other. We have Fleming's left hand rule. All right, our thumb and index fingers are 90 degrees to each other. Our index finger and our second finger are 90 degrees to each other. And if you were to look at this, you're going to see that your thumb and your second finger are also at 90 degrees to each other. Ow. It really hurts to do that with this hand. All right, so Fleming's left-hand rule, this is what we use to determine force on a conductor. Let's remove this again. So using Fleming's left-hand rule, we know that a magnetic field will produce a force on a current carrying conductor. We know this is big revision. We're doing really fast crash revision, right? You all know if you were to put a current carrying conductor in a magnetic field, right? So if your current carrying conductor, meaning a conductor that's carrying a current, if you put it within a magnetic field, right, symbol for magnetic field is B, it is going to experience some sort of force. Your wire is going to move up or down, left or right, or an angle, depending on the direction of your field and the direction of your current. So that sounds familiar, right? We did that in CSEC. That's why I flew through it really quickly. If it sounds a little hazy, go revise your book. All right. So we have force, we have current, and we have magnetic field strength or magnetic induction, magnetic flux density. So let's read this again. Using Fleming's left-hand rule, we know that magnetic field will produce a force on a current carrying conductor. The angle the conductor makes with the field will change the force acting on it. So this is where we're going to have a little bit more of details when we look at how Fleming's left-hand rule works. At CSEC, we just looked at the fact that it works. But please know that these must always be at right angles. All of your forces here to get your maximum effect must be at 90 degrees to have your maximum force exerted on a wire. Fleming's left-hand rule tells you about force being exerted on a current carrying conductor. So when let's look at diagram 1. When your wire is at an angle to the magnetic field is given here by B, that's your flux density or magnetic induction B. Or at our level, we just say it as how strong your magnetic field is. If you wanted to work out how strong magnetic fields are, we do have a unit for it. There is a quantity that we measure, and that's going to be in Teslas. So if we have our current carrying conductor carrying a current of I, and it's passing through a magnetic field at some angle, it's going to experience a force, all right? We'll check Fleming's left-hand rule just now to check our forces. All right, if we have a current carrying conductor here with our magnetic field going left to right, all right, so we're coming out of the north and into the south, so this is the direction of our magnetic field, and our current is going down. All right, if our current is going down, we want to work out which is our direction of so our current here is going down. We want to work out where is our force going to act. So you all, let's try that. The best way you all do this is to always line up your magnetic field. Magnetic field is the first thing you line up. So you line up your magnetic field. All right, remember I'm the opposite angle to you probably. You're going to look at your current. Current is going to go down. Okay, this is really hard to see with that. All right, current is going to be going down, and then you release your thumb, and it's going to be coming. All right, the force is going to be coming towards us. Are you all seeing that? Let's try that again. To apply Fleming's left-hand rule to this question, or this instance, we have a current coming down. We have our magnetic field going across. And we want to work out what is the force on this wire. The force on the wire is going to be a maximum since they're all at 90 degrees to each other. So how do we determine what direction of force? Using our left hand. Remember, my video is reversed to you all, so my left hand looks like my right. All right? So first thing, I always tell people, line up your index finger with the direction of your field. All right? So with my board, what I'm seeing, my hand is lined up, start, end. All right, current is going down. So you turn your hand to make sure that your second finger is facing the current of the direction of your current. Let's see if I can get this better. Aha! Kind of. Right? Current is going down, and all you have to do is release your thumb and realize that the force is moving out of the page, all right, and towards you. You all seeing that? You getting that? Don't let me have to pull up video on everybody and see what you're doing, you know. We can do that. For Fleming's left-hand rule to work, everybody has to be at right angles or to work the best. Your forces and your angles and your currents must all be at 90 degrees of each other for these to work. If they're not at 90 degrees each other, they're going to be somewhat less. And here we have, if our current is in the same direction as our magnetic field, nothing's going to happen. Right? Absolutely nothing's going to happen because you will end up with zero force. Now, why are you going to end up with zero force? The mathematics is going to tell us why. And let's look at the mathematics now. All right, force is given by the equation of force is equal to Bill, where we have B is your magnetic flux. All right, so that's your flux or your magnetic strength in simple terms. I is your current, as we read down here. I is your current, as we read down here, and L is the length of your conductor. All right, please note this must be in meters, your current must be in amps, and your force will end up being in newtons. You have to remain this, and the unit of flux density is, magnetic flux is the Tesla. So force is equal to Bill, B-I-L, you know. This is only when we have a maximum force. At a maximum force, we will have force is equal to Bill. But if you were to consider this, we always must take into consideration now an angle. As we saw here, your conductor can lie at an angle to your conductor and your magnetic field. They don't always exist at right angles to each other. Sometimes they act as angles. So we can take this angle into consideration. All right, reading down. When the conductor is at an angle to the field, we have, let's just think about this, we have conventional current. Please know that all our rules are using conventional current because they did not determine the nature of the electron and the nature of electricity until after all these rules were devised. So we use conventional current. We have our magnetic field flowing from left to right, and your conductor makes an angle of theta degrees to your magnetic field. Now, your magnetic field in a regular plane magnetic field will all be parallel and not horizontal, but they will be parallel to each other and straight. So your magnetic field will always tend to be in straight lines. So when your current carrying conductor acts at an angle, we have to take this angle into consideration. So we are going to get force is equal to BIL sine theta, where theta is the angle your wire makes with the magnetic field. All right, so whatever angle your wire makes with the magnetic field. So here you cannot say the horizontal. The horizontal is a wrong word because suppose we end up having our magnetic field, right, in different angles and different directions. Suppose this is our magnetic field, right? Suppose this is our current carrying conductor. You're going to have to work out the angle it makes with your field. All right, so don't always just assume horizontal. No, you want to get the angle between your current carrying conductor or your wire and your magnetic field. Now here we can determine why your force is maximum when theta is 90 degrees. You all work it out, get your calculator and tell me what is sine of 90?
That's not 1.
That is 1. what is sine of any number below 90? Wouldn't it be a fraction?
Yeah.
What is sine of any number above 90? Wouldn't it also now just be a negative fraction?
Yeah, but I think you don't get around the calculator for that.
Seriously, work out sine of 120 for me right now. Tell me what you get.
I guess 0.87.
0.87 is not negative there. Sine curve.
Nah, I never get negative.
Or is negative when you're beyond 180. Sorry. All right, these ways have to remember your theta. Yes.
Why sine?
Why sine?
Yeah.
And as opposed to cosine.
Yeah.
All right. Just going back to resolution of angles, resolution of forces. Where do we take sine and where do we take cosine?
Sine is when you move away. Moving away. Yeah.
No, sine is when you're moving towards the horizontal.
And we have force, and we'll have F sine and F cosine. Remember that?
Oh, yeah.
All right. So
Yeah.
to where it is moving, we will take sine of your angle. We're not going to take this upper part. We're just going to take how far it moves away from your angle or from your magnetic field. Let's draw that. That's a good explanation. Why didn't I think about that before? All right. If this is your magnetic field in any direction whatsoever, all right, and let's take our magnetic field as your x-axis, and this is your current conductor. Is going to be acting at an angle. So say it's acting at some angle. So your current conductor, your current carrying conductor would have moved theta degrees away from your magnetic field. So this is where we end up using sine theta, because sine theta tells how far you moved away from your x-axis or your, well, in this case, your horizontal. But remember, we don't have a horizontal, but we are taking our magnetic field as our x-axis, right? So that's just how we do this. Just to go back from regular mathematics or from unit 1. So this is why, you know, I tell you all your physics come together. Unit 2 is where they all come together. All right, so we will take cosine, we will take sine theta since we are moving away from the magnetic field. And we usually know the magnetic field. We don't know what the force is, and we want to work out the force. So this is why we take sine of it. So if I have sine of 90 is equal to 1, right? Oh, there, that's not working. All right. In the waiting room, I have seen, no, I not seen him in the waiting room. Oh, there he is. Okay. Why didn't that come up? Oh, well, it's right here next to me. Okay, so we have here, generally the equation is force is equal to Bill sine theta. And when theta is equal to 90 degrees, you're going to get sine theta is equal to 1. And there's no other time sine theta can be larger than 1. And that usually happens at 90. You all should know your sine curves, right? All right, know your sine curve. If you don't know your sine curve, you're going to know it when we do an AC theory. All right, so sine theta is at a maximum at 90 degrees, maximum at 360 plus 90, 450, minimum at 270, and whatnot. So anything between above, other than 90, you're going to get a fraction, and you're going to get less force, because when you multiply any number by a fraction, you're going to get a smaller number. So this is going to lead us to our proper definition. All right, coming from our definition of force is equal to Bill. All right, so let's remember it's force is equal to Bill. And if we were to manipulate this a little bit, you will get B is equal to force over current by length of your conductor. So now considering that, let's read the actual definition of a Tesla. So 1 Tesla is the magnetic flux density of a field in which 1 Newton acts on a 1 meter length of conductor, which is carrying a current of 1 amp and is perpendicular to the field. So simply 1 Tesla is the strength of magnetic field. So if you had your magnetic field and your magnetic field had a strength of 1 Tesla, and you had a current carrying conductor carrying 1 amp of current, then that means this this wire will experience a force of 1 Newton. So they all have to be ones to work it out. Everybody, that made sense now? Who's messaging me? Okay. Rashad, your message now came in. All right, so let's continue. It is useful to know that the magnetic flux patterns, to know the magnetic flux patterns of various current carrying conductors. So we have to know 1, a long straight wire. So here we're going to look at 2 long straight wires in different directions. Then we have to look at plain circular coil and then a solenoid. So here we're going to reintroduce to you or reacquaint you with a law you should know, a rule you should know. You all know. Anybody wants to make a guess what RHGR is?
Right hand something rule.
Grip.
Right hand grip rule. All right, so we have the right hand grip rule or the corkscrew rule, right? Where if we took a wire, so we have here a long straight wire, and you have to know how the magnetic field behaves in a long straight wire. So we have here 2 instances. We have one where our current is going up, and 2 where our current is going down. So I want you all to take your pen, right? And if you take your pen and you grab this and go down, so if this is your pen and your thumb is facing down, your fingers are going to wrap in what direction around your pen? It's going to wrap
Clockwise.
clockwise. Well, did I just say down? Right, this is the down one, sorry. All right, it is going to wrap clockwise around your pen. You all see that? If you look at it, your fingers are actually moving in direction that a clock's hands would move. That's what clockwise means. And if you're going up, I have it completely different here to the diagram, don't worry. And you try it going up, you're going to realize that your field is moving in the opposite direction. So it's going to be moving anti-clockwise or counterclockwise. So that's what we have here on the diagram. Just please, note how to use these things very quickly and, well, very quickly. And it reaches the point you don't even have to take your hands and do the rules. You could just take it there and just use your finger on the pen and you'll get it out easily without having to make all those weird signs in the air. All right, so when the current is going up, you have counterclockwise magnetic field. So once your current is going up, you're going to get counterclockwise magnetic field. Once your current is going down, you are going to get a clockwise field. That's all you have to remember. Please note, I don't think I have it written down here, but you all can note, we do have 2 symbols that represent which direction your wire is flowing into a page, because your paper are 2-dimensional, but we live in a 3D space. So we do have 2 symbols that represent where our direction, our current flows. All right, so if our current is coming out of the page, it's represented with a circle and a dot. And if it's going into the page, meaning your exam paper that's right in front of you or your question paper that's right in front of you. And if it's going into the page, it will be a circle with an X. Just find, cute ways to remember it. You all wouldn't believe I think I told my Form 5s last year how I remember which one is which. And it's the funniest little story. Anybody remember that story?
Is it when you're digging for treasure or something?
Yeah, the pirates thing, right? What I came up with it. Well, I love Pirates of the Caribbean, y'all. Love it, love it, love it. So I remember this. Whenever pirates have to go and look for treasure, they have a treasure map. It's always an X on the spot. And don't we dig down into the ground, right? Into the ground to find buried treasure. So it's the same. I'm pretty sure that's what they came up with too. Don't hold me to that, but still. So I always remember the X means to go down and into the something or into your page. And the other one is the opposite. So you just have to find funny little ways to remember your things. We call these memory tools, right? Astronomy people, remember I tell you we love to tell stories or find different ways to remember things. It plays in every single subject. So moving on. So this is easy to remember. You don't even have to remember this. Just apply the right-hand grip rule. Plain circular coil. This is an extension of the application of the right-hand grip rule. All right, so let's look and see how this is an extension of the right-hand grip rule. So let's just think I have a page, right? And I have a current, wires come and be leafed here. So this is where my battery will be set up, right? I have my positive and my negative battery set up here. So I have my positive and I have my negative. Current is going to come out on one side. It's just making one loop, and then it's going to go down into the other side. Let's take a funny color that you'll be able to see. All right. So coming out using your right-hand grip rule, you're going to realize that your current is moving. Let's get a really big marker for this. Your current is going to be moving counterclockwise. Everybody agrees with that? Coming out of the page. All right, so it's going to all be moving counterclockwise. Well, it's coming out of the page. Now, when it's going into the page, all right, so this is here where we're going to use the grip rule to go in. You're going to realize we'll have clockwise motion. All right, so taking clockwise motion, let's just get a clockwise motion happening here. Clockwise motion, it's going to be moving in the opposite direction. But let's look at this. If we take our fields and extend it outwards, let's take our fields and extend it outwards. Do you see how those two poles, those two wires will result in a pole forming? Because you're going to see your magnetic field going in. This is your magnetic field going in at one direction, and then it's coming out through the other direction. You all can see how your magnetic field is going to end up forming not a current, but a flow of magnetism where we are all, both sides, doesn't matter which direction you're coming from, your magnetic field is going into one side of the coil, and it is exiting the next side of the coil. Everybody sees that? How it kind of flows together, because at the end of the day, the both of them pass each other with the same direction. They're not moving in opposite directions when they pass each other. So this is how we end up getting a magnetic, we can end up getting poles in a solenoid or a coil. So with one single coil here, let's erase this and see if we can find it, see it simply. So here I'm going to have my anti-clockwise motion, Then I'm going to have I didn't change the pen. Right, my clockwise motion is going to be flowing in the opposite direction. And by just extending that, you're going to realize that they both carry, if we were to put a magnetic field or if we were to put iron filings, they're both going to get attracted into one direction. And if you were to put like your plotting compass here would point this direction here. right? It will go towards the magnetic field. And if I were to put my plotting compass here, it will be moving out of your field. So this is going in to your field, and this is coming out of your field. So here we're not just only going to get two circular looking magnetic fields. These two circular magnetic fields are going to essentially end up looking like this: a north and a south, where something flows out of one pole and goes into the next. So that's what we have happening here. We have a south happening on one side and a north happening on the next side. Why I'm saying that right now? Because that leads us to the very next section. The very next section is a long solenoid, and our long solenoid can be used to produce a magnetic field, a solid magnetic field. We're not talking about two circular magnetic fields that were going on here. Right? A single wire produces a circular magnetic field. What I want with a circular magnetic field, I don't want no circular magnetic field. Look, Fleming's left-hand rule, right-hand rule operates on the premise that we are moving in straight lines. So how on earth are we going to get straight lines from a circular magnetic field? What we do there, by introducing multiple lines or multiple wires, right, into a solenoid. Now, what is a solenoid? A solenoid is just simply one wire wrapped around a nice concentric coils. Now, by wrapping around these things in the concentric coils, we are going to take what we had up here in the diagram before. So this is our concentric coil. Let's see if I can go up. All right, we're going to get our concentric coils, and we're going to just extend it to produce a solenoid. So what we're going to have, instead of just one coil, we're going to have a next coil, a next one, a next one. And what happens, each one is going to produce the same thing at the base, where they have this little circular field existing at the base. All right, so all will have a circular field existing at the base. And by having a circular field existing at the base, we are going to encourage your magnetic field to flow through. Let's get a big marker for that. You're going to encourage your magnetic field to flow through your entire coil system. So what we do, just by having multiple wires, these individual wires, they are going to contribute to building up a magnetic field, which is what we have in a solenoid. A solenoid creates a magnetic field, a measurable and very strong magnetic field. So a long solenoid is basically a large collection of circular coils. So the pattern is quite similar. In fact, it is possible to locate a north and south pole in a solenoid. So here I have current. Let's zoom into this one and see if we can follow it. All right, we're going to zoom right up into this one, see if we can follow it. All right, so let's look at this. You're going to realize that your current is coming, going. If we had this, your current is coming out of the, where'd my pen go? It's going to come out and then go back in. So this is what's going to happen. You're going to have this happening. All right, your current is coming out and going into your wire. All right, coming out and going into the page. So if I had the next one here, this is what my coil will actually look like if I had nothing else. All right, and my current is flowing through my coil. And what happens at the base of the page, or at the base of each of these coils? Now we're talking about, even though the coil is a three-dimensional shape and a three-dimensional structure, all right, this is what a coil looks like. It's not enough to say you have a middle. What we do, if you were to imagine that we had a straight line drawn across the middle, like what we did for the page, right, you are going to get currents and you're going to get currents coming out and then going in. You're going to get currents coming out and then going in. So you're going to get that field thing that we just had happening with one singular coil happening multiple times. And by happening multiple times, we are going to have the cumulative effect of all those fields adding up together, because the nice thing about magnetic fields, they're not individual fields. They add up to each other. So one field is going to help, well, for solenoids they do. All right, so your fields add up. And what happens, this flow that we had spoken about is going to end up resulting in an actual measurable force, magnetic field. So we have the field going in one direction and come on out the next. If you were to extend this, go up even further, we can get a small one come through here. We're going to get a field that goes into one side and comes out the next. We could get even a bigger one. All right, we have a field that comes out of one side and goes out the next. And we know that north flows into south. So here where it is flowing out of, you're going to have a north pole forming, and where we have it going into, here we can see it's going out, and your north pole always, your magnetic field comes out of your north pole and it flows into your south pole. So you're going to end up with a south pole forming. So this is how we are able to tell where your north and south poles are in a solenoid, simply by looking at the direction of current. Now we do have rules to learn to make this simpler, because I don't think we're going to go in exams and take our wire, draw our wire, figure out where all our fields are and work it out. No, that's going to be too long. We do have rules to learn and to determine where our current forms, where our magnetic fields form, and whatnot. So you all can see how a solenoid becomes essentially like a magnet. A basic magnet behaves like this, where we have the south pole, we have the north pole, your magnetic field comes out of one side and goes into the next. All right, similarly, next direction, that's what your magnet looks like. And these are what solenoids look like once they're carrying current. If they don't carry current, then nothing's happening. You need the current to be moving. You need current to exist in your wire to create this magnetic field. And this just happens instantly. Any piece of wire we can have any wire, any metal wire. As soon as we run a current through it, it creates a magnetic field around it. This is why we have the topic of electromagnetism. One cannot exist without the other. We create the electricity that we use in our homes from magnetism, right? We have magnetism here being produced by electricity. So they all do tie together. One results in the other, to the point where you can't say we had this first. You will not have electricity first and then magnetism, or you will not have magnetism first and then electricity. They both tie to each other. They both result in each other. They're very, very, very similar down to the core, meaning if you were to look at how atoms behave, right? If you look at how atoms behaved, that's how we end up seeing where our magnetism arises. It comes from the very base of all our materials. Okay? So that's our field. You have to learn the field, what the field looks like for a flat circular coil, and we just did the flat circular coil. All right, so this is our flat circular coil. So you have one circle on the next side, the next circle on the other, and there is an area of influence or an area of flow between them. We have our plane conductor, our plane wire. Our plane wire has just your current going around, your magnetic field going around it. Why is my thing not working? Okay. And then we have our solenoid. Our solenoid ends up behaving like a magnet because we actually have a measurable and appreciable north pole forming, and we have a measurable south pole forming. So that's the three instances we're going to have to use. Obviously, if we're going to look at the behavior of a magnetic field in a wire, a single flat coil, and a solenoid, we have to be able to work out how strong your magnetic fields are in these three instances, which is what we're going to go on to next. So we have to calculate for calculate your flux density for a circular coil, a very long straight wire, and then a very long solenoid. Now we use these words of very long for a reason, and we're going to come to that just now. All right, so let's just go through this, how to calculate your flux density. You're not required by any means to learn the proofs for these. I didn't learn the proofs of these until second year university, so you don't need to know them. You just need to know how to use them. So I have here for a circular coil, one circular coil or a flat circular coil. We're not talking about a solenoid. We're just talking about a wire that, is tightly wound. I'm sure you all have seen coils that are like this, where they appear almost flat. All right, so if you were to look at them at the side, they look really, really flat. So you have your current going in and your current coming out, and it's going to create a magnetic field. So let's work out, how do you determine the magnetic field? All right, in this situation. So you're going to have B, which is your flux density, is equal to mu naught. Mu naught here, it is not epsilon naught. This is mu naught. Please note our word, it is the permeability of free space, not the permittivity. Please note our two different words. One is permeability and one is permittivity. Permeability is how easily a magnetic field can pass through a material. Now remember, magnetic fields can pass through almost any material. Electric fields cannot pass through almost any material because you do have insulators. But a magnetic field can pass through anything. And we did it in school, and you all use the two super strong magnets that I have, and you could have put it on both sides of your hand. You all remember that? Whoever was there for that play?
Yeah, the neodymium magnets.
Yeah, right? Use the neomagnets. The magnetic field will pass through your hand. So it's different than electrical fields. Electrical fields require either a vacuum of space or they require a medium to pass through, like a conductor. Not magnetism. Magnetism can flow through a material because it moves the space around them. So here we're going to have the word permittivity, not permittivity, the permeability of free space, and that is given by 4 pi by 10 to the minus 7 Henry per meter. Henry is another unit. We will not touch what a Henry is, but if you want, you can go and look it up. All right, so it's 4 pi by 10 to the minus 7 Henry per meter. Then we have N being your number of coils. Since this is a circular coil or flat coil, this number will be pretty low. We're not looking at big numbers like 500 and 700. We're probably looking at like 20 or 10 or 15 or something. Then we have current, obviously current, because we're looking at force is equal to bill, always works. And radius of your coil. R will be the radius. You can use capital or common. I don't know why they use different. Oh no, it's supposed to be common. It just self-capitalized. We'll just like to harass us. All right, so we have here for a flat circular coil, obviously if we have a radius R, the entire diameter of your circular coil will be 2R. So how we work this out? B is equal to mu naught Ni over 2R. For a long straight wire, it can be shown that the magnetic flux density for a long straight wire, remember, if my wire is here and it's producing a magnetic field around it because of how strong my current is. Do you all think the magnetic field at A will be equal to the magnetic field at B?
Must repeat that?
Do you think the magnetic field at A will be the same as the magnetic field at B?
No,
No.
well, it will be weaker at B.
You all know this. doesn't magnetism decrease the further away you go from the magnet?
Right, yes.
Yeah, because if you bring two magnets really close to each other, right, they are going to influence each other. So that means the further away you go from a magnet, the less the influence will be, or the less the strong the magnetic field will be. Which is a statement of which rule again? Or which law again? Starts with I.
Have a man by the name of I in physics.
No, there are nobody named I in physics. Well, actually there is, but there's a law that states or tells us what happens when something gets smaller as we move away from the source.
Pertaining to magnetism.
Anything.
Inductive effect or something.
No. We use this a lot in Unit 1. What law?
Is the inverse
Thank you.
relationship?
The inverse square law. Right? The inverse square law tells us the further away you go from something, right, the smaller the intensity or the smaller the effect of that field. So if I were to put, say if this was our current carrying conductor, very close to it, if I was very, very close to my current carrying conductor, say I put some magnetic, I put some small bits of metal filings, iron filings, they might get attracted to the wire, right? Or they might form a very nice, strong magnetic field pattern. But suppose I go some distance away. This is my regular wire carrying 10 amps of current, and I'm going to go 1 meter away from my wire. I am barely going to even see a few bits of iron filings forming a pattern. Why? Because the magnetic field is so weak, far away from my field lines or from my current line, that you would not have a very strong influence. So this is where we say, this is again an application of the inverse square law, as in when you go, the further away you go from something, the smaller your field is going to be. And let's look at that. What is our equation for this here? Our equation here for infinitely long wire. Now, when we mean infinitely long, we're not talking about a billion meters. We're probably looking at like 10 meters. Right? Not looking too far. Infinitely long could be like around 10 meters long wire, if so much. If your wire is long, your magnetic flux density is given by the equation of mu naught I. Mu is your permeability of free space. So 4 pi by 10 to the 7 minus 7 by your current could be like 10 amps, divided by 2 pi A. 2 pi A just being the area or the circumference of your, around your wire. If this is your wire and your magnetic field formed around it, when 2 pi A or 2 pi R be your circumference? Anybody? What is the circumference of a circle? Nah, boy.
Not 2 pi R?
Yes. Right. His circumference is circle with 2 pi R.
And the area is pi R squared.
Yes.
Right.
Right. So that's your first equation. Remember, you're just required to learn them. All you have to do is learn them. You don't have to find any sort of proof or whatnot. And our last equation we have there for a very long solenoid. Very long solenoid is something that has a lot of coils, like the solenoid or the spring we use in school, right, with a lot of curls. That is a horrible looking solenoid, but whatever. All right, very long with a lot of coils in them. And how do we work out your magnetic flux density or your flux density for a very long solenoid? It's going to be mu naught N being N is your number of turns in your coil or number of coils. I is your current. And L here is going to be the length of your conductor. So what it's going to look at, the more coils we have in a length, right? So if you have a lot of coils in a long length, you're going to end up getting a certain amount of magnetic fields happening. So we have a term to learn here. Capital N is your number of turns. L is the length of your conductor. L is equal to the length. But we can go ahead and make up a new term where common N is the number of turns per unit length, or number of turns in 1 meter. All right, so N is the number of turns in 1 meter. So rather than having B is equal to mu naught Ni over L, we can go and pull this out and replace it with common N. So we could take this out and replace it with common N. And we're going to end up getting magnetic flux density is equal to mu naught N common Ni. Or we call this Bunny. This is your Bunny equation. We just had Bill, now we have a Bunny equation. See, I'll tell you some of our equations will work out to words. Later down, we'll have Barney. All right, we will see Barney later down, I think. So next equation that sounds like a word or sounds like, whatever, we have the Bunny equation. Bunny equation tells us what is the magnetic field strength. Not the magnetic flux density, magnetic flux density of a very long solenoid is given by Bunny, where B is your magnetic flux density, mu naught is the permeability of free space, N is the number of turns per meter, and I will be your current. Now, there's a way to learn how to work with this, and we're going to encounter this in questions, because sometimes they tell you it has 500 turns in 20 centimeters. And that's where you have to learn to determine whether or not you're going to use common N or you're going to use N over L. Both ways, we're going to see how to use them. So don't worry about it too much. And please note, a coil can be considered to be infinitely long if L is more than 20 R. So if this is your solenoid, all right, if this is your solenoid, all right, very long solenoid, and the length of your solenoid is more than 20 times the radius of your solenoid, it's considered to be infinitely long. Why it's infinitely long? When they work out the mathematics, I think they introduced infinity in there somewhere and something cancels with each other. So just remember, they will ask you, when can a coil be considered to be infinitely long? Once the length of the coil is more than 20 times the diameter, not the diameter, 20 times the radius of your solenoid. So that is it for here. We're going to wrap up here. I did say we're going to stop at 3. We're going to continue next day with magnetic forces. So if you will, please read up on, revise your other rules. We did already left-hand rule. Go and revise what is the Fleming's right-hand rule. Read up on the Earth's magnetic field and the Van Allen's radiation belt, because I will not be going through that. This is a topic for you all to read. And I did tell you all in university, nobody's teaching you. You have to go and do 3/4 of the work, 90% of the work on your own. So I'm going to let you do some work on your own. You need to read up on the Van Allen's belt. Now, it's been a very, very long time since the Van Allen's belt has come. So the longer this takes, the more possible this question is going to show up. All right, so next day, we're going to do forces on a charge. We're going to look at the Hall effect. So if you want to read ahead, please, you all print your handout, write out your handout, read your handout in advance. So the next day.
I was reading up on that.
Good, great.
I see it on Google.
All right, Hall effect is a very popular question. It's giveaway marks question. Extremely popular question. It can only come in like 2 variants. So.
But there's not some in electronics.
Yeah. And what do you think is the base of electronics? The way how electricity and magnetism behaves.
Yeah, right. Yeah.
So we are going to more fundamental parts of the electronics. even though our whole next module is electronics. So let's wrap up there. First,